So my great pleasure is to introduce our industry keynote. So we have András Vajda from Ericsson. He's born from Cluj, Romania. He's Hungarian and now living in Finland. So it covers pretty much the vertical part of Europe. No. Okay. As the title says here, he's an expert in cloud computing in Ericsson's global cloud computing program, and he has had several positions in Ericsson. He's been in Ericsson Research and Networks business units. So he's been involved in base stations, developing base stations, contributed to mobile devices and so on. He's also active in global scientific community. He's been involved in several conferences and international initiatives. He's involved in IP, and he authored a book called Programming Many-Core Chips, which has been out since 2011. So I would welcome András to provide the keynote, and the stage is yours.
Thank you. So that makes sure I can skip the next slide, because Jarmo said it all. By the way, this is the coolest place. It's hot off the bunker, but here it's, I might move back. Alright, so Jarmo said most of it. Basically, what I'm most proud of is that I've had the chance to work on real products with large-scale products with many processors, lots of lines of code, lots of bugs, and all that stuff. And if you want to know more, you can take a look at my blog. Every now and then I tweet something. Right, a disclaimer before going into the presentation. This is not an Ericsson presentation. It talks about my own views, and those probably don't match with what Ericsson would officially say. I will probably make claims you will disagree with. That was my purpose. As an excuse, I am told many times that I'm wrong, so that's probably, and that has been proven before, so I hope that's a good excuse if I say something you don't believe it's correct. That said, this will not be a scientific talk. It's based on what we see in the industry happening, what we believe should happen next, or we believe will happen, even though it might not be the best thing in the world. As the title said, I will try to bring some ideas from cloud computing to embedded systems, because Ericsson, essentially, it's an embedded systems company, even though those embedded systems tend to be large systems. Still, by definition, they are embedded systems. We are moving into clouds, because that's what the technology evolution and the market demands us to do. So we have some insights into both domains. Few things we are seeing. I call this the binary world, meaning that sooner than later, everything, the world will become bipolar, meaning that computing systems will either be connected embedded devices, and you will have phones, cars, medical devices, all that stuff, or will run in some kind of centralized elastic execution environment. You can call that cloud. And then, of course, you will still preserve some connectivity between the two, but there's not much else left in between. Things are, either moving to end devices or moving to a central place. At the same time, the number of compute platforms is reducing. Companies that used to be big are going away, and we are left with very few computing platforms that really matter. And now again, this is from an industry point of view. If you really look careful, I believe there are 2 or 3 that will survive. Of course, the x86 world, which dominates this part. The low power, I call it the ARM world, that dominates this one. And then maybe GPUs and some niche players. But that's pretty much it, what will survive, and that also applies to networking. This stuff used to be specialized hardware. It's becoming more and more x86, maybe some network processors here and there surviving, but that's about it. I have a good example of high-end digital signal processors for media processing. That used to be a big market, but they were so successful that they basically put them out of business, because all the world needs in terms of high-end media processing DSPs, it's maybe a few tens of thousands per year, and that's not the market to go after. Finally, and this we see more and more, the world is becoming more homogeneous. Heterogeneity is good, its performance is better, but the software is becoming so complex, and the cost of hardware design goes up so much that these actually are more important than optimal performance. If you take a look at what companies are doing, they want uniformity, they want simplicity, even at the cost of performance. Time to market beats performance. So that's what we see happening, and this applies across the board. Now, relating the two worlds together, they are not that different. That we realized quite easily, and of course this is a bit of oversimplification. But if you look at the cloud side, how a cloud is built up is out of several data centers. Inside the data center you have a network fabric that connects your storage and servers. The servers have some memory, and that is basically that's how you build from hardware perspective a cloud. If you compare that with a many-core chip, it's a very similar build-up at a smaller scale. So what is a server in a data center? It's roughly equivalent to a core, server memory to cache, storage to memory, on-chip interconnect, and so forth. So we see that things that work nicely in cloud will work fairly well in a many-core setting, and vice versa. And I have a couple of examples where we actually did that, moved learnings from one domain to the other. Some more claims around this. For one thing is that it's a lot of discussion, talk about power efficiency. We believe that energy is more important than power. Total energy you consume to perform a task is more important than your power, meaning energy per second. So basically what we are seeing, and it's a practice for many of our products, is to burn more power if the result is achieved in a shorter time. That's a better solution. The other thing, and this comes from the cloud domain, but we see it also in the embedded domain with the chips with lot of cores, is that compute and storage will be free, or at least very low cost compared to the cost of moving bits around. What really matters is how you get access to your data, how you move your data to where it needs to be used. And actually the volume of data that we generate or we need to handle is growing faster than the technology for moving it around. And that's one thing that is good to keep in mind. Third, as I already mentioned, cost of software makes suboptimal performance the new normal. The quest is not for optimal performance anymore. The quest is for controlling your cost and reducing your time to market. So it's actually it's okay to waste capacity if that brings you faster to market, while fulfilling also the first goal, consuming less energy. And finally, what we are seeing in the embedded domain is that virtualization is slowly creeping into non-obvious areas. because it's the best solution we have so far for preserving legacy. We see GPUs virtualized, we see DSPs virtualized, and all that happens because it's a way to preserve your legacy and again control your cost. Alright, so then a few lessons from this. For us, the first lesson was to embrace virtualization. It's, as far as we can tell, is the best technology for consolidating workloads without changing the software. And if you look around, all major ISAs support virtualization, have protection domains for enabling virtualized systems. And really the point here is that you have all these fancy or strange real-time and so forth operating systems that you cannot get rid of. So what you can do to keep them alive is to try to collocate them with other operating systems. And virtualization embedded systems is not that different from data center enabled systems, with three differences that we have seen. One is support for real-time workloads and operating systems, and that's really one of the key differences. If you take data center virtualization, there is no such thing as real-time workload, it's all best effort. Here, that matters, and that's what makes it special and makes the hypervisors a bit different. Of course, the footprint is smaller, but that's usually not, it's a problem that usually it goes away by itself. And then the third one is that it's not enough to support virtualized Linux and Windows. You have all these legacy operating systems that need to continue to work. And this is already a reality for many systems, for telecom systems, for game consoles, mobile phones, and as you probably know, also for GPUs, it's being introduced. It's a way to consolidating workloads and taking advantage of newer processors. So this is one that I think will come down to embedded systems, or it's coming down. The second one is to move computations, not data. This is my favorite subject, and it has an interesting history. We've been doing some research into this, both at Ericsson and together with Chalmers. There was, while working on that, there was a paper actually that Yale and some others published around this a few years back. And the whole idea is that if shuffling data around is expensive and can have and you need to take care of consistency, it's better than to move the computation to where the data is. Keep the data locked somewhere up and then move the computation there. In a data center, what is common practice is that you have data stored somewhere. When then you have a mechanism to detect when that data needs to be accessed, and then your virtual machine that is trying to access that data is moved to that place and it's executed near the data. If there are several virtual machines trying to access that, you can have a simple consistency model preserving the consistency of the data by using a scheduler that allows exclusive execution. We started looking at something like this for some of our products. Then we saw that this happening in the data center, so we took some lessons and experimented with it in an embedded system. Basically, what the adaptation looks like is that you lock the data to the cache of one of the cores, and then you move the execution of your task to that core when needed. And as I will show on the next slide, one interesting side effect of this is that you can actually skip cache coherence altogether, still preserve the shared memory model, and also save power or energy. So why do this? Currently, on a chip, the shared memory model relies on cache coherence, bringing memory blocks to where the code needs it. It's fairly complex. With more cores, it gets more complex, both design and verification-wise. And it only solves the easier part of the problem. From a programmer point of view, this is a given. It has to work, but still the programmer needs to design and use synchronization mechanism in order to have semantically correct software. Just having coherent caches doesn't guarantee that my two threads will not mess up my data. This effort is not exploited by hardware in any meaningful way, so why don't we try to do something about it? The solution is that we can let the software define how caches are used and how the shared memory is obtained without getting too much into the hardware details. How would you organize such a hardware? In a data center, it's easy. Each compute node has a storage that it controls. There are no consistency synchronization mechanism between compute nodes, and there is an infrastructure, and how it's realized is irrelevant for moving computations around between any nodes. On a many-core chip, this would mean that each core has local associated cache. There is no coherence between these distributed caches, but it's still, of course, possible to move computations around inside the chip. It's possible to communicate between cores on what needs to be executed. How do you achieve shared memory in this case? If you really look at what programmers do, they use synchronization mechanisms. They essentially define transactions that should be mutually exclusive. To get sharing, I call that sharing transaction. To get that, they either use locks or mutexes or similar things. The acquisition marks the start of the transaction and the release marks the end of the transaction. In a transactional memory solution, the beginning and the end obviously mark the transaction. So having these transactions available, these are actually pins about areas in the program that will access shared resources. So if we know which shared resources will be accessed, then the compiler, runtime system, and hardware have enough knowledge to fix the rest. How it's fixed is basically the following, and this works for any number of cores and any number of shared data. Basically, what happens is that related code fragments that access related data structures are grouped into what we call transaction groups. And each transaction group is assigned to one core that we call the guardian core. So think of it like this. I have a number of these kind of sharing transactions. They access data. If those two transactions access two different memory areas, then they can be put on different cores. If those memory areas are in some way related, then those transactions have to execute on the same core to get semantically correct execution. The compiler, having these markings available from the programmer, can detect this kind of groupings, and it can generate code so that those sharing transactions are executed on the correct core. So whenever such a transaction is entered, the execution is moved to the core that owns the data that transaction will access. On the guardian core, you can maintain a hardware queue of tasks that are waiting to be executed, and that actually has a neat side effect that you can have prefetching of the data to cache. So if you have, it happens that guardian core needs to guard a lot of data, if you have a queue of tasks that wait to access that data or part of that data, and knowing which part of that data each task will access, you can do prefetching ahead of the transaction. And that's something that happens also in data centers. There are mechanisms that evolve this further. If you have nested transactions, you might end up in deadlocks, but there are mechanisms to actually automatically detect and resolve those deadlocks. I will not go into details, but it's based on tracking. If Guardian cores start communicating, and whenever you detect a cycle of Guardian cores waiting on each other, that's when you have a deadlock and you need to resolve it. And this again can be done in hardware if needed. In a cloud setting, we did this in software. Within a chip, it can be done in hardware. What's the benefit is that for the programmer, there is no need to worry about synchronization and deadlocks. All the programmer needs to do is to indicate where shared data is accessed, which parts of the code and which data. For the chip, it can do away with cache coherence. And actually, if you dig into this, the consequence here is that the hardware adapts to the needs of the software. Some cores will get dedicated roles. They own some part of the memory areas. They take care of bringing that onto the chip, into the cache, modifying it, writing it back, and so forth. Some simulations you have seen that the cache hit ratio actually goes up significantly because you can do prefetching. This was one area that drew inspiration from how things happening in the data center. The third one, let's say, if it transitions to first, is wasting resources. What people do usually when they write an application for a data center is that they create virtual machines. So one model that happens often is that you create all the virtual machines you might ever need. You let them just linger around, and then you use them whenever needed, which sounds a bit like a waste of resources. But if your goal is to complete a task in as short time as possible and at minimum energy level, then perhaps it's okay to waste some computations if it helps complete your main task faster and at lower energy level. And what the cloud guys always say, that's compute is cheap, go ahead and then use it. The real question is then how you waste it, how do you actually use it. So this is another piece of, this is in research still, it's not in commercial use in any way. One insight is that even if an application has strong sequential dependencies, depending on the type of the input data, the space of possible execution paths might be limited. And I'll show you an example on the next slide. With a certain probability, one of these paths is the correct one. If you have the right hardware and runtime system support, this can be exploited. And it's something that people typically do in some applications. It's not uncommon to launch in a cloud setting virtual machines that do pre-calculation of data, store it somewhere, and then it's used whenever it's needed. Sometimes it's not needed at all, then it's a wasted effort, but it was worth a try. So here's an example to illustrate what I mean. It's a simple one and well-known Huffman decoding. How Huffman compression actually, not just coding, works is that if you want to compress a string, you calculate the frequencies of the symbols, you build a tree that allows you to allocate shorter codes to more frequent symbols. So in this case, A is most frequent, so it will get just the 1-bit code. D is the least frequent, so it will get the three-digit code 0, 0, 0. So left or right means 0 or 1. Then you take that one, you compress it, and you end up with this string. The problem is decompression, which is traditionally hard to parallelize. Intuitively, it would be nice to use some kind of data parallelism, chunk up this data and decode it in parallel. But how the heck you know where there is a code boundary here? This is all you see, is it here, or is it here, or is it there, or where is the code boundary? I cannot chop it up into pieces. But what you can do is to take a look at your code tree. And basically, if you take this example, if you go 2 levels deep, so you look at how many symbols I have at up to 2 levels deep in this graph, then I have the symbol A and the symbol B that together appear 23 times, and that's roughly 89% of all the cases, which means that with the 89% probability, in a distance of 2 bits, there is a code boundary. So if I can reason like this, then what I can do is I apply data parallelism, but for each chunk, I chunk it up in this case in 4 pieces, but for each chunk, I don't just decompress start decompression parallel from the first one. I start it on the first position and the next one. I start 2 threads, two parallel decompressions. And with the probability of 89%, one of them is correct. One of them will be obviously wrong, maybe even correct, but maybe wrong. If you really reverse engineer this, you will see that thread 0, thread 3, and thread 5, they are actually successful. So this 89% is actually in this particular case turns out to be 100%. So I ran 6 threads. 3 of them were wasted work, but 3 of them were successful. So I reduced the execution time 4 times. I used I wasted 3 threads, but I had 4 times better performance in decompression. So this I call probabilistic data parallelism. You can use data parallelism, but you have an uncertainty on where you actually chunk up your data. So then, basically, you get the probable speed up on K cores with the P probability according to wrong, that should be P. So, not N, but P. So, basically, and in the Huffman decoding case, this is done on a Tylera chip. You get a pretty nice, depending on the data, up to 10 times speed up on 60 cores, which doesn't sound terribly impressive, but this is achieved at constant energy consumption. The energy consumption is the same, and it still runs up to 10 times faster. You waste a lot of effort, but you get a speed up, and your total energy consumption is the same. The power is of course higher because you have 60 cores working. So, with that, this is an area that we continue looking at. How can waste of resources actually help us do some things better? So, looking back again, what we learned from cloud and or that we got reconfirmed from the cloud area is that, first of all, compute resources are plentiful. Interconnect and data consistency is costly and complex. It's very true in a data center, and as we all know, it's true in an embedded system too. Total energy is more important than power. We are constantly reminded, including our customers. It's okay, they have reliable power sources, but they don't want to pay the energy bill. Infinite resources and elasticization of resources enable controlled and educated waste in order to address the first 2 concerns. If I can work under the assumption that I have a lot of resources and I can, fire them up and kill them down as I need, then I can think differently about my problem. and come up with new solutions. And speculative execution, as I showed in the previous slide, recomputation of values and so forth, those are possible ideas. And ending up with the last thing, or the first thing I started with, virtualization is proven to be powerful technology that will move into this domain, and its main use is really consolidating workloads, preserving legacy, and enabling elasticity in terms of what kind of execution resources I can offer the programmer, and taking advantage of statistical multiplexing. How will embedded systems look like? From what we can see over the next years, we will see virtualization will be virtualized. And again, before saying anything more, this, let's say, the mainstream, not necessarily for every niche domain. So there will be niche domains where this will not be correct, but we see those niche domains becoming smaller and smaller islands, while the mainstream will look a bit like this. Those embedded systems will look more like mini data centers with a lot of computing resources, with bottlenecks around moving data back and forth. Can be more wasteful because we have enough capacity to maybe do things that are not optimal. At the same time, will be orders of magnitude more complex software-wise. We did a small analysis of how complex a GSM system was compared to an LTE system, radio base station, and it's around 100 times more software, and that's a time span of 20 years. And many of these will simply be extensions of a central data center, meaning that we will see many of the embedded systems connected, network connected, and there will be a fluid moving around of computations between these devices and the central data center somewhere. As a parenthesis, many of you perhaps know about the Eurocloud project. It's a European research project. One of the driving forces for one of the industrial partners, Nokia, as far as I understood, was to create an environment that looks the same in the mobile phone as well as in the data center, so they can shift workloads around more easily. And that's why homogenization will, that's one of the reasons why homogenization of compute environments will continue. We will have fewer and fewer and less esoteric compute environments. Because of this, the network connectivity, and because of software complexity. I think we are a bit ahead of time, but that's my final slide. If you have any questions.
So this gives us some time for questions.
Well, I was wondering about the energy consumption. Okay, the fact that we can have a slightly increased power consumption, but we can process our data faster, and so the energy will be lower.
Yeah.
But on the other hand, when the power is increased, then the heat is increased,
Yeah.
and the life of the chip in embedded systems becomes shorter. Right.
Sure.
So, is there any way of industry to overcome this problem by making more robust systems, except for just putting fans on the on the processor, right?
Well, yeah. So one thing that it's not only that you do it faster. One thing that we do design ourselves chips is to run them at a much lower frequency. Have many of them and run them at lower frequency, which means that you get also less power consumption and less heat. through that. That being said, I'm not a chip designer, so I cannot answer if there are techniques around for mitigating the heat in a better way. I think there are more people in the room that could answer that. From a company point of view, using those chips, we assume that those chips can work at their maximum built-in capacity. What we do here is that you use them at maybe maximum capacity for a while, then you shut it down partly, for example. The ARM's little big or big little idea, having a big core and a small core, actually uses the same idea. Run the big core, as long as you need, then shut it down and put the stuff on the small core. It's the same idea.
Yeah.
There's a question.
So you mentioned that computing and storage is becoming very cheap, right?
Yeah.
So wouldn't there be a point in the future that is cheap enough that you can store more things locally and you don't need the cloud anymore?
That's a good, yes. Yes, and the answer is yes. That reminds me of a talk by a now non-existent Sony Ericsson CTO who has shown how much storage you would need to record all your senses all the time during your lifetime. So basically everything you see, touch, smell, everything, record all that, all the data reaching your brain. And I don't remember the figure, but it wasn't that much. And he claimed that within 5 years that will be possible to have in your mobile phone. So your mobile phone could record all you experience. So yes, it will be possible. But what that will mean is that what you perceive, or the data that's in your mobile phone, it will be very hard to move that somewhere else. So you will have to come up with some clever ideas how to, maybe things you would do in the data center you will move to your mobile phone, because it's still better to burn the battery on the processor than send all that data over the air.
Other questions?
There are.
Sorry.
Another question about the speculation.
Yes.
So, I wonder how scalable this approach is going to be, because at some point you run out of probability, right? So,
Right.
if you need to use up more, use more computing resource, at some point you really can't push speculation.
So, okay, I think it will depend on your application. In this particular case, it's, well, not linear, but logarithmically linear, if that exists. I don't think it exists. It keeps increasing, and it depends on the size of your data. Of course, if you compress a small amount of data, after a while you cannot chop it up further. But if you compress 1 gigabyte and you need to decompress that,
That's actually what I was asking, because my impression about the cloud is that they do compress and decompress on a block basis, right? For probably exactly for that reason. But for embedded, sometimes there's a latency sensitivity and so on, and you may or may not be able to chop things up and so on.
Yes.
And so I'm just wondering, from your perspective, in practice, do people really go into more of these block-oriented approach, or they really push the speculation as hard as they can?
So they do, and I can give you one concrete example. Is the radio base station, the baseband processing. One of the, I didn't get into that, but one of the big problems there is that the nature of the problem is so that in one half a millisecond interval you have 100 senders sending a very small amount of data, and in the next interval you might have one who wants to send a lot, and you need to process that when it's hundreds. It's easy to parallelize, do it in parallel. When you have one big guy, then it gets harder to parallelize, and that's exactly where actually trying to predict what happens next and do some pre-computation or some kind of probabilistic assuming becomes more important, because your resource that you want to optimize for is your efficient use of your radio. It's not your baseband processing DSP. That can burn more power if you use more efficiently the radio, and the operator's customer gets better experience. It's one example of where compute is cheap because something else is more valuable.
There was a question there.
Yes, so you made a parallel between data centers and chips, and another feature you find in data centers with the cloud is the ability to reconfigure the topology of the network. You can move around cables and switches, if you will, and you change the...
You don't do that.
Well,
You don't want to do that.
you don't want to, but if you want to optimize the interconnect to given applications, that's being done.
I mean, in the data center, if the hardware works, you don't want to touch it. That's kind of what operations guys say. Don't touch it. It works. Don't touch it. It's complex enough. So what happens in data center is that you get virtual overlays and overlays and
modular
so
virtualization of the network. Yes. But
Yes.
what you see is that you do have virtual topologies.
Right. That you do see. Yes.
Yes.
Yeah.
So let's focus on that.
Right.
I think that's an essential feature for not only performance but basically isolation, which is the ability to reason about a portion of the network or a portion of the resources and have a physical insurance that it is actually separated, even though it's virtualization mechanism, it's still isolation mechanism. What kind of equivalent features you would expect from on-chip networks to achieve something similar?
Right. That's a good question. So. I cannot talk, unfortunately, about what we do in our chips, but if you take a look at, for example, Tylera's chip, they have what they call virtual channels. You can define virtual channels between two or several of your cores over the interconnect that is isolated from the rest, which is, in a way, network virtualization, on-chip network virtualization. That could be one example.
But you do expect it to be a general features of future embedded systems?
I think eventually yes, if you will be required to isolate your workloads on the chip. If you will have workloads that will need isolation, you will have to have something like that.
One more question here.
I have a question about the cache coherence problem.
Yeah.
Because sometimes shared data are not only in the transaction, right? The program can share data out of the transaction, and also you can have fault sharing.
Absolutely.
Fault sharing, like
fault sharing, yes.
So this is a problem, and you cannot forget about the coherence for this data out of the transactions. And the second thing is about the programmer saying when it's going to need some data and it's not going to need it. This is not making harder the work for the programmer.
Well, no, because if you look today, cache coherence, let's say it's a given thing, but when you write a program in C, for example, you will still have to put locks around the data that you share between your threads. You will have to do that. You don't get away from that. Today you don't tell the underlying system, why do I acquire this lock here? Do I acquire it because I will access that chunk of data, or do I acquire it for some other reason? What we are saying here is that if you add that information, what will be the data? Why do I acquire this lock? Why do I need to synchronize with another thread? It's because I will modify this data and I know that that thread will also potentially modify it. If you add that information to your locking or transactional memory or whatever, then that enables your runtime system to say, aha, it's that data. So instead of bringing it here and keeping it coherent with the other caches, I know here you acquire the lock, here you terminate the lock. The part between those two, I will move you to that core where the data is always there. It never leaves that core. It's never copied here to this, maybe for read, but there it gets complicated when you bring reading into the picture. There are two ways to do that.
Okay, that concludes the keynote. Thank you very much.